Okay, let's go ahead and get started for today. This is class 2, and today what we're going to do is we did a little bit of sort of foundational work last time with some stuff with sets, and we're going to kind of continue along those lines today with some central concepts of formal languages. And if you remember that from last time, we had sets, we had some set operations. We're going to see some of those again, but today we're going to talk about the central concepts of formal languages, meaning like what is a language. So let's go ahead and get started today. So the first thing here, before we get into what is a language, is we need to define this concept of what would be known as an alphabet. That also in some literature you might see that referred to as a character class, but the alphabet is essentially defined as a finite, non-empty set of symbols. So one thing to notice about that is it doesn't say what those symbols are. It's just as long as it's finite, you can't have an infinite-sized alphabet. You also can't have an empty alphabet. It has to have at least one symbol. But notice that leaves a whole lot of room for different possibilities there. So for example, there's some examples down there, binary numbers. And notice that we tend to represent the alphabet with this uppercase sigma. That's essentially a lot of the formal languages will use that, but it could also be represented with a like a different symbol or even a word, like a defined word. But we're going to tend to use that uppercase sigma in here to represent alphabet. So here, for example, you could define an alphabet being 0 and 1. Like the binary alphabet, you could define it A, B, C, D, E, F, or A through Z. And notice when I'm defining these, since it is just a set, we can use this curly bracket notation and just list the elements in there. Notice we could not, however, use the ellipsis and a ... at the end like you would with sets, because alphabets are not allowed to be infinite. They have to be finite. So here's 0 through 9. Notice it doesn't have to be characters like we're used to thinking. It could be things like this. Really, it could be anything that you have this finite, non-empty set of symbols. It could be all of the ASCII characters. So it could be a large set, or it could be small. You could have as few as 1 symbols in the alphabet, but you could have a whole lot. It just cannot be infinite. Okay, a string. A string is a finite sequence of symbols chosen from some alphabet. And there's one other definition that we want to get in here as well besides a string, and that is that the concept of the word over. And so notice we have that if a string has only symbols from some given alphabet, then that string is said to be over that alphabet. So for example, down here, this string with zeros and ones, that would be over this alphabet. It would also be over that alphabet. It would be over this first one and the fourth one. It's over each of those, but it's not over this one, this one, this one, or this one, and that one. It is over the ASCII characters as well. So one thing about strings quickly, though, is notice it's a sequence. It's not a set. It's a sequence. So you can have duplicates, like 0, 0, 0. There are multiple A's in here. There's 2 3's in there. And the sequence of those, the order of them matters in that case. Also notice there's no curly braces representing that, because again, it's not a set, it's a sequence. All right, now one special string is called the empty string, and that's a string that has 0 symbols in it. If we go back, you'll notice that this just says it's finite, but it doesn't say it's non-empty. So you can have an empty sequence, a sequence with nothing in it, or 0 symbols in it. And to denote that, we're going to use this lambda. Sometimes you'll see this little epsilon thing used. But we're going to, in this class, tend to use lambda over here. But if you might see literature and online material that uses this, it's really just a way to denote a string with no symbols in it. Now, the length of a string is how many symbols are in that particular string. And the way we represent that is with these vertical bars, just like we did the size of a set. That also is used on strings to represent the length. So here, if the string is defined as this string of 0s and 1s, then the length of that would be 8. The length of lambda would be 0. So that's a string with length 0 in it, or with no symbols in it, so the length of it would be 0. Okay. Now, for convenience, we can use lowercase letters as kind of names for strings. And notice that we're doing that here, like W equal. So W itself is not a string. You can think of that kind of like a variable or a name that represents some string. In this case, we could define it specifically as 10101, or V as blah, or U as ABBA, or T as lambda. These are all strings that we're defining or assigning to a particular name, or assigning a name to. And that is done for convenience, so we don't have to write these out multiple times. And sometimes later on we'll see this will be done to abstract the concept of a string. We're going to say, assume that W is a string of symbols over some given alphabet, and then we'll use that to prove things about that particular string, or the particular pattern that makes that string, or something like that. Okay, so string operations, just like we had set operations, there are string operations. And we're going to go through a few of these here. The first one is concatenation. And concatenation, if you're used to programming languages, you're probably used to that. You basically take one string and another string, and you stick them together to make a new string. So in this case, for example, if we have W is some sequence of symbols, A1, A2, all the way to AN, and V is another string of symbols, B1 through BN. We could probably make this an M, because this is implying that they have the same length, but they don't have to. But if we concatenate those, W and V, it's basically a new string of symbols that starts with the first one of W, goes all the way through it, and then immediately following that is the first one of V, and then goes all the way through it to the end. So an example down here would be W is high, V is there. We concatenate them. Notice there's no space or anything between them. It just becomes hi there, all run together. And we could concatenate them in the other order as well. And then we'll get another string that way. And that's an important thing to note. In that case, we'll get there hi, again, no space. And one thing to note is WV is not necessarily the same as VW. In other words, that concatenation operation could give a different result depending on which order you perform the concatenation. And that makes sense. It's probably something you're used to seeing. All right, another string operation is string reverse, which is denoted by this raising some string to the R. So this is the reverse of that. And basically all that does is it switches the order and reverses it so it's backwards. So rather than being A through N, it starts with N, or 1 through N, it goes N down to 1. So in other words, in my example down here, if we have W is stonks, then when we reverse that, we put the last character first, second to last one next, and it just goes backwards through that string. All right, another string operation is exponentiation. And in exponentiation, you basically take a string and you raise it to some power, as you can see here. So W, if it's defined as A1 through N, W2, it goes A1 through N, and then it repeats it, A1 through N. And this, if you're used to like programming in a language like, I don't know, let's say Python, this is kind of like string repetition in there, where you multiply a string by a number and it repeats it that number of times. So in other words, W to the 2 is that string W concatenated with itself 2 times, W3 is 3 times, and so forth. And as an example here, we have blah, W raised to the 3rd power, exponentiated to the 3rd power, blah, blah, blah. Again, no spaces between them because we're just concatenating it with itself, this total number of times that we see right here. Okay, a couple other definitions here related to strings. The prefix of a string, the suffix of a string, the substring of a string, and a subsequence of a string. So a prefix is any string that would result from removing 0 or more symbols off the end of that string. So in other words, it's a string of a group of symbols that start some string, but maybe complete it, maybe don't, because we're allowed to remove 0. So in other words, if, for example, my string was prefix, then a prefix, this is confusing, let me pick something else. Let's say my string was central, Then prefixes of that would be central itself, that we remove 0 symbols off of it. It might be centra, it might be center with a ending with an R, it might be cent, C-E-N, C-E-C, and it could also be lambda, because we could remove all of the symbols and leave nothing left. Suffix is the same thing, but at the end. Substring, we remove 0 or more symbols from the beginning and or the end. So pretty much you can cut off a prefix, cut off a suffix, and what's left in the middle would be a substring. Now a subsequence is a little bit different. With a subsequence, we're removing 0 or more symbols from anywhere within the string. So for example, ET would be a subsequence, but not a substring, and it's not a prefix and it's not a suffix, but ENT is a substring and also a subsequence. All right, now there's one more version of these prefix, suffix, substring, and subsequence things that we should be concerned with, and that is there's a version of those called the proper version of those. A proper prefix, proper suffix, proper substring, proper subsequence. And those are the same as the normal version. In other words, we're still removing symbols from the end or the beginning, or the end and the beginning and the middle. The only difference between those is that we have to remove at least one. In other words, it's not 0 or more, it becomes 1 or more. And we're not allowed to remove all of them. We're not allowed to have it be just lambda left over. So those are the only two differences. So proper prefix is going to be shorter than the original string, but not length 0. And that's true for all of those. Okay, now powers of an alphabet. Notice that this is a little bit different than exponentiating a string, because we're exponentiating a set, because an alphabet is just a finite, non-empty set of symbols. And notice that we can take that alphabet and we can raise it to a power. And what that does, the one way to think about that is it produces a set of all strings of length n that are over that alphabet. So for example, if I have this alphabet defined as the set A and B, just two elements in that, then alphabet raised to the 0 is all strings of length 0 over that alphabet. In this case, it's just going to be lambda. That's the only string that has length 0. But if I say, what's the alphabet raised to the 1, that's just going to be the set AB. Now notice that's the same set we had up here, but these are a little bit different in that when you take an alphabet and raise it to a power, it always produces strings. So this is the string A, just A. This is the string B. This is the symbol A and the symbol B. So they're not really quite the same, because as soon as we exponentiate or raise an alphabet to a power, we get a set of strings. And in this case, those strings are one symbol each. Now, if we go to 2, what are all the possible strings over alphabet that are length 2? Well, we have to account for every possibility. So AA, AB, BA, BB, and alphabet to the 3 is all of them that are length 3, and we have to account for every possibility in that. Length 4, alphabet to the 4 would be length 4, and so forth. So in other words, when we raise an alphabet to a power, it produces a set of strings. All right, now, taking that concept and continuing with it, there are two things that we want to define here. One of them is called this clean star, or sometimes called the clean closure, sometimes just called star. But essentially, and clean is really not the right way to pronounce that. The mathematician / computer scientist who came up with this didn't pronounce it that way, as Kleiny, but we're going to call it clean in here, or we'll probably just end up calling it star. Kleiny, something like that. But anyway, that alphabet raised to the star produces the set of all strings of any length over that alphabet. And the formal definition of that is alphabet to the star is equal to the union of alphabet raised to the I, where we vary I from 0 all the way up to infinity. So in other words, we union alphabet 0, which if we go back, remember that was lambda, with alphabet 1, with alphabet 2, with alphabet 3, and we do that infinitely with all of them. We union them all together, which in other words, we're getting a set of strings of length 0, and all the ones of length 1, and all the ones of length 2, and all the ones of length 3, and 4, and 5, and so forth, all the way through infinity. So in other words, alphabet star is going to result in an infinite-sized set that's going to be all the strings of any length from 0 to infinity that we could ever produce over some given alphabet. So if we were to go back for just a second, if I have alphabet as defined as A and B, then alphabet star is going to be any combination of A's and B's formed together into a string that we could ever make, including 0 of them, meaning lambda, all the way up to as many as we could ever imagine, up to infinity. So the size of this set is always going to be infinite. Now, positive closure is closely related to that. It's the same thing, but it's all strings of length greater than 0 over that alphabet. In other words, it's the same as what we have here, but we just take off the alphabet to the 0. And if we think about what that means, going back here a second, it's the same, it just doesn't have lambda in it. So in other words, we have to have at least one symbol, or 2, or 3, or 4, but we're not lambda, not 0 symbols. So same definition, the only thing it changed was I starts at 1 rather than starting at 0. Okay, so now we're up to a point where we are almost ready to define a language. One other thing to notice is that if we think about the relationship between those, the only difference is the inclusion of lambda. So alphabet star is the same as alphabet plus union with lambda. So in other words, if we take all of them except for lambda and we add lambda to that, we now have the star version. And conversely, if we take plus, then that's the same as star, take the lambda away. So this is a set difference. So we're taking the lambda away from that set. What that will leave is everything alphabet to the 1 through infinity, which is the definition of plus. So those have that relationship with one another. Now we're finally up to the definition of a language. And a language, remember that's one of the phrases that makes up the name of this class. It's Automata and Formal Languages. You can kind of see it up here. And so it's going to be important for us to use this a formal definition for what we mean by a language. And you might be used to thinking of languages as being like English or Spanish or French or something like that. Mandarin. There's a whole bunch of spoken languages. Or you might be used to thinking of it or hearing it used in terms of like C++ or Java or Python or Ruby or something like that with programming languages. But in this is a formal language class, so it really doesn't mean any of that. And in our case, a language in formal languages is just defined as a set of strings over some alphabet. And notice that a language is just a set of strings, and it has to be a set of strings over some particular alphabet. And remember, an alphabet has to be finite and non-empty. So a language is a set of strings over that alphabet. Now, every language has some defined alphabet. That's part of the definition that we have up here. And every string in a language is an element of that alphabet raised to the star. Because remember, that thing raised to the star is representing all of the possible strings we could make over that particular alphabet. Anything from 0 up to infinity worth of things. So every string that we find over that defined alphabet or in the language has to be a member of that set. And notice along those lines that languages can be finite or they could be infinite. So you could have a language that has no strings in it. That's still part of the possibility. That would be called the empty language, a language that's an empty set. Notice it doesn't say it has to be non-empty. It's just a set of strings. So the empty set is a language. We could have a finite language that has like just one string in it, or 2, or 5, or 100, or 1,000, or a billion. It can be finite, but you can also have infinite size languages that have an arbitrary number of strings in them. All right, so a few languages. So as some examples, let's look at these. So all strings in the form a to the n concatenated with b to the n. And remember that a is a string here. We're concatenating with itself n times. We have b, we're concatenating it with itself also n times, and that's the n's are the same. So that means we have a string that has a certain number of a's followed by the same number of b's. And here it says where n is greater than or equal to 0. So if n is 0, a to the 0 gives lambda, b to the 0 gives lambda. So empty string plus empty string, 0 symbols plus 0 is still 0, so that gives us lambda. But n could be 1. So there's 1a followed by 1b, and it could be 2. There's 2a's followed by 2b's, 3, 4, and dot, dot, dot. That could have any arbitrary number of a's. So notice that this language is infinite, and that's okay. All right, the next example, all strings with the same number of a's and b's. Now notice this does that. You might think, well, that's the same thing we just defined. But notice this one, the a's have to come first, and the b's have to come second, but with the same number, it doesn't say which one has to come first and which one has to come after that. So this one, the A could come first and then the B, or the B and then the A, or A, but they don't have to be necessarily, the A's don't have to be together, the B's don't have to, we have to, if we count up the A's and the B's, we have to get the same number of them. And so notice this one's also infinite. So any string that you think of where the same number of A's and B's. And notice that the languages, this might not be specific enough, because notice it doesn't say anything about what about C's and D's and other smiley faces and other weird symbols. It doesn't say anything in my language or English language description of that here. But I've kind of just made the assumption that we're only talking about A's and B's. So this is one of the needs for formal languages, is it's going to allow us to not use an English language sentence like we have listed here, but it's going to allow us to have a very formal definition of what that exact set that we're talking about is, or that exact language that we're talking about. So all strings of A's and B's with length exactly 3. Well, here they are here. Notice this one's finite. The other two were infinite. This one's finite. All positive even numbers, 2, 4, 6, 8, so forth. That can be considered a language. Prime numbers, 1, 2, 3, 5, 7, 11, 13, 17, and so forth. That could be considered a language. So notice that languages here can kind of be numerical like this, because does this fit the definition? Is this a set of things over some sort of fixed alphabet? Yeah, all of the things that come out of this are going to be 0 through 9, and there's a certain set associated with that, the set of prime numbers, the set of positive even numbers, and so forth. Okay, since languages are really just sets, that means we can use those setformers that we saw previously to define them, and define them in a more specific way than these kind of English language-like descriptions that we used over here. So the setformer basically works like it did with other set. You say something like W, such that, and then some description that defines what W is. And we put that in curly braces. So over here, like where we listed out these with dot, 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 with the ellipsis and curly braces, that might not, or we tried to write an English language description of it. In some cases, it might be better to use one of these setformers. They're more precise to use a setformer. So here, all strings W such that W is a positive even integer. All strings W such that the length of W is even. Now, a lot of times we would have a defined alphabet that goes with this as well. And that could be either part of the problem domain that we're working in. For example, if we're dealing with digits, that it would be understood that the alphabet would be 0 through 9. If we're dealing with like letters of the alphabet, we might have A through Z. But notice that we could have something that's a little more loose like this, all strings W such that W is a valid zip code. And then we could have more formal mathematical type things where A to the N, B to the N, where N is greater than 0. Or A to the N, B to the M, where N is greater than M. In other words, where we have more A's than we have B's. So these are all done with a kind of the set form notation. Remember when you read these, you would say all strings W and the colon. Sometimes that's written as like a vertical bar, like this length of thing. I'll try to avoid that in this class because the vertical bar is used for length. But you read that colon as such that, and then read the rest of the description after that. And we can do that because languages are really just sets of strings over some alphabet. All right. Now, because languages are just sets, that also means we can perform some operations on them that are typical set operations that we saw before, like union, intersection, difference. But there's another one here that we didn't see before, that's language concatenation. So with language concatenation, if we have two languages, L and M, then concatenating those two languages together results in a new language. So just like up here. So if we union a language with another language, we get a new language. And here's the definition of that. So union, we take all the strings from L and all the strings from M, and we put them together into this new language, and it's all strings S or W or whatever variable we want to use over here, such that S is an element of the first one, or it's also okay if it's an element of the second one. And since it's a set, you don't have duplicates. You wouldn't have any repeats in there. And intersection is the same, except it has all strings S such that S is in both of them. If it's in both, they are overlapping, and so it ends up in the resulting language. And then difference, that works the same as it did before. It has to be in the first one, but we take away any of them that are in the second one. It has to be in the first one, but not in the second one. And then we put it in this one. Now, concatenation is a little bit different. They would say all strings in the form ST, such that, so this is a string that kind of has two parts. It has the S part, and maybe I should reverse the way I'm doing this because it's backwards on the camera as you're looking at. So it has like the first part, and then it's got the second part. And that first part we're saying is S, that has to come from, that's all strings where the first part comes from L and the second part comes from M. So in other words, we're looking at any possible string that could result where the first half of it is from L and the second half of it is from M. And so essentially we're creating a new set of strings there that all have to fit that. So in other words, you can think of it as every possible combination of items from L and M, how they could, any way we could combine them together to make new strings by concatenating them. And that makes a new language. And then we have this clean closure and positive closure again, but performed on a language instead of an alphabet. And basically what we do there is we say language star is the same as the union of all of those from 0 to infinity. In other words, that set of strings concatenated with itself that many times. So if we took, for example, the language that just consisted of high, and we did a star on that, so we said take that language that is the string hi and do a star, we get lambda, we get high, we get high, 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 and so forth. We get just an arbitrary number of those stuck together all the way up to infinite. So this is going to result in an infinite size language always, and same thing with positive. The only difference is no lambda. Okay, so continuing on from that. Oops. Actually, that might be where we're done for the day. We had that slide repeated twice, but this is a relatively short lecture. What I'm going to do is there will be a quiz, so either, well, on a combination of the stuff from this lecture and the previous one, but the idea here is kind of, we got through that more quickly than I'd intended. And the idea here is that what I want you to do here is think about and study each of these things. So in other words, prefix, suffix, substring, subsequence, proper versions of those. Like look at all of those, go through the slides, look at all those, and there will be a quiz over this. It's posted to the course site. But the main thing that I want you to get out of this is this concept of languages, that it's just a set of strings, and then that there are these there's a whole bunch of ways to define those, from really simple ones to really complicated infinite-sized ones, really simple infinite-sized ones, And then there are these operations we can perform in those languages, which all result in a new language. And so that's it for today. Be ready for that quiz to show up. And the quizzes will be on Blackboard, on the Blackboard course site. So I want you to take those on there. They do have a time limit, so you should probably be prepared before you take that quiz. And depending on the nature of the quiz, some of it will be multiple choice, some of it may be fill in the blank or short answer kind of things. So just be prepared for that. And then next class, we're going to start looking at languages a little more carefully, ways of defining those languages that in a more, how should I say it, a more formal way, kind of like we were doing back here with the Setformers, and ways of manipulating languages. And that's going to lead us to our first set of automata, or machines, shortly following that. And we're going to make machines that actually act as ways of defining or recognizing if a string belongs to a language or not, which is actually pretty cool. And the cool thing about this is, since language, notice that definition of languages covers a really wide range of stuff, everything from all English sentences, or all valid programs written in JavaScript, or all zip codes, or all valid phone numbers. All of those things are languages. And since we have abstracted that to mean just any set of strings over some alphabet, the cool thing is that means that when we get to making those, or coming up with ways of defining those, or making those machines that recognize strings in those languages, that's going to give us a technique that we can use anywhere where you have some sort of language or a pattern of symbols that we want to recognize. All right, so we'll go ahead and stop there. Everybody stay safe. And next class, study that stuff, and then just be prepared for that quiz.